Good day, my name is Trent Shepherd and this is my presentation of my geotechnical desktop study for the proposed dam and reservoir project assessment 2 for UNISA Geology 3701 2026. Project overview and summary. The dam aims to provide water security and support small-scale irrigation to the local rural population in the Guamatipa and Racapola area in Limpopo. Since no site investigation has yet happened, this assessment is based entirely on published geological maps and other online sources. It flags the likely ground conditions and lays out the proposed field and lab work needed before detailed design can begin. Firstly, I'd like to clarify an assumption I have made about the site coordinates. The original coordinates place the dam wall on a steep hillside and the reservoir center in the middle of a rural settlement. I adjusted these slightly, placing them between the original coordinates to more accurately reflect the likely location of a small-scale dam and reservoir basin along the watercourse, as shown on this slide. This has no impact on the geology discussed in this presentation or the report, since the regional geology is fairly consistent across the area, but the revised coordinates allow for a more appropriate analysis of the proposed dam project. Climate and regional rainfall. The site falls within a semi-arid tepe climate, what's classified as BSH on the Köppen scale. Rainfall here is highly seasonal, with most of the roughly 550 mils a year coming down between October and March as intense summer storms, while winters stay dry with the odd bit of frost. Geotechnically speaking, this means summer saturation drives erosion, while winter drying triggers shrink-swell behavior in the clay soils. From a geology point of view, the site sits on the eastern limb of the Bushveld Igneous Complex, one of the largest layered intrusions in the world. The bedrock here belongs to the Rustenburg layered suite, and the area's shape is largely down to two structural features: the Steelport pericline, a regional fold, and the Steelport fault, which has played a major role in how the rock has deformed over time. Putting that into a cross-sectional view, the valley sides, where the abutments of the wall may sit, likely have pyroxenite bedrock close to the surface, but the valley floor, right where the wall needs to cross the watercourse, is mapped as deep compressible quaternary alluvium. I should reiterate that this is based on the desktop mapping and online data available and not on-site testing, so it's an assumption at this stage. Still, it points to the core engineering challenge here, to put stiff rock foundations on the side of the watercourse and a soft, yielding one in the middle, which raises the risk for differential settlement. The table shown sets out what each material may mean for the design. Residual clays may be expansive or dispersive. Colluvium has variable strength and may need to be removed. Alluvium is the least favorable of the materials, needing treatment before anything can be done on top of it. Weathered bedrock is variable as well, and only competent bedrock is truly ideal, though even there, joints and fractures in the rock can still affect seepage and need to be checked during the field investigations. 4 problem soils are anticipated at the site. Expansive soils, which are residual clays derived from the mafic bedrock, showed plasticity index values of 17 to 49 in tests done elsewhere in the Steelport area, so there is the potential for a shrink-swell risk at the site. Dispersive soils are vulnerable to internal erosion and piping once water gets into them. Collapsible soils can settle suddenly the first time they become saturated, and the compressible alluvium in the valley floor can settle under just the weight of the dam wall alone. Because the Bushveld complex is a layered intrusion, the bedrock here could possibly show horizontal igneous layering, vertical cooling joints that may break it into blocks, and given how close the site is to the Steelport fault, it could potentially have shear zones and deeper weathering as well. If present, these discontinuities would matter because they could control the strength of the rock and potentially act as pathways for groundwater seepage below the proposed dam. This desktop geological report makes up phase 1 of the process, which is now complete. Phase 2 would be the intrusive fieldwork stage, which I'll discuss in the next slide in a little bit more detail, but it will determine the actual conditions on site. Phase 3 would then involve the lab testing of those samples to get the real engineering numbers. And finally, phase 4, which uses that data to complete the detailed design of the dam wall. Field program covers 3 main areas. Trial pits across the basin and valley floor will log the soil profile and collect samples. Boreholes along the wall depth Along the wall alignment will confirm the depth of the competent bedrock and pick up any deep discontinuities. In situ testing on the boreholes and cores will give live permeability results along with detailed joint spacing and infill. In the lab, the soils go through a few different tests. Particle size and Adderberg limit testing classifies the soil types. Dispersivity testing checks how easily it erodes in water, and shear strength and compaction testing looks at whether the soil is suitable for use as fill. Rock cores go through their own set of tests, namely uniaxial compressive strength testing, which measures how much load the rock can bear, and point load testing, which gives a quicker estimate of that same strength, and finally slate durability testing, which checks how well the weathered rock holds up when exposed to wetting and drying. All of this needs to happen safely and legally, which means working under the Occupational Health and Safety Act, the Construction Regulations, National Water Act, and NEMA, with sediment control in place to protect the watercourse during these investigations. And so finally, with the risks mapped and the compliance framework in place, this study concludes that the site is a suitable candidate for further investigation and is ready to move on to that next field phase. Thank you, and that's the end of my presentation.